Okay,
What?
okay, we should get started.
So you reset all the passwords?
Right, to the password on my luggage. So, we're going to continue on to chapter 2. Hopefully this will be the last time we have to do just straight book learning, and then we can actually start doing some programming after this chapter. We could have done a little here, but it would have been pretty complicated. But we'll get to something about processes next time. We are just cruising through chapter 1 and 2 because there's a lot of introductory material. So just, I guess, sit down and enjoy. All right, we're going to talk about a lot of stuff. Basically when the system's booting up and how do we actually interface from a process into the operating system. Yeah, that's nice. Okay. All right, you have a user interface. Hopefully you are used to this. You have your GUI and then you have your command line interface. Let's see, program execution. Right, it has to be able to load your program into memory, which means it needs to take what's on their disk. Your program resides in disk, copy into memory, set up a bunch of environment variables, and then kick it off. Actually, what happens is they create the operating system creates the process, and then the first thing that happens is a page fault because your program's not in memory, and then it goes and loads it in memory. So you got I/O and file system manipulation, and also services that are provided by the operating system. They're not something that you have to particularly code yourself, which is nice. No, you can go ahead and tell us.
Is the slideshow or the PowerPoint you just put up on GitHub yesterday, not this one? Is that something else random?
This is chapter 2. Is it not on GitHub?
Now there's some like T words,
There's some T words.
some kernel-y stuff.
Ooh, kernel-y stuff. Oh, Tannenbaum and Torvaldist?
Yeah, that one.
Okay, we'll get to that, don't worry. But you don't have these slides right now that you want to look at? Ooh, that was close. SL. Terrible program to run. Lectures, PowerPoints.
You keep the lectures and PowerPoints on GitHub, right?
Yeah.
And on Blackboard you're just posting the
Ooh.
homework stuff.
So book slides. And we'll push that. Oh, yeah. Why do I have a feeling this cord is not going to work? Yeah, it didn't work. All right, I'll have to put those up.
What are you plugged into down there?
I'm plugged into this guy. Someone else can give me a network.
Over there?
That'd be nice. Reaches. Well, that's hopefully recognizing. Let's see. This is a more expanded view from last time of what the operating system is. Remember, you have your hardware at the bottom. That's not part of the operating system. That comes from your hardware manufacturer. And then right on top of the operating system, namely your kernel. But you will, on the low level, usually provides a bunch of different capabilities: program execution, I/O operations, file systems, communication, resource allocation, accounting, error, and protection. Notice that that is part of the operating system, and then via system calls is how it interfaces between those low-level directives that we'll be learning about here to different tools that you're used to, maybe a command line or a GUI. And usually the command line and GUI is considered part of the operating system. Sometimes it's not, depending on who you talk to. But definitely the system call level down to right above the hardware is always part of the operating system. So you need to be able to communicate, usually, well, between processes or different computers. It can be done through shared memory or message passing. Ooh, what do those two sound like? So two processes can communicate by sharing memory or doing message passing. Y'all done any of this before?
Is that symmetric and asymmetric?
It's symmetric multi-processing is what you're thinking. So asymmetric and symmetric messaging.
Yeah.
So that has to do with message passing. So then there's also shared memory. Have we ever done shared memory map, or
We were talking about it. We did do a memory map.
is there any time where you have multiple execution paths that share memory?
You said multiple execution paths. You're talking about threads?
Yeah, so you can have threads. And do threads share memory? Well, okay, that was a rhetorical question. So threads share memory. Sorry. Yeah, so threads do share memory, so that's a shared memory model. A thread is not a process, but you can set it up to where processes can share memory, or they can communicate by passing messages, like over a network, for example. Error detection, a lot of things, hopefully you can tell a lot of things can go wrong. So it needs to, the OS needs to be ready for this to mess up, hardware to fail, I/O devices to just either die, or maybe the user unplugged their USB key at the wrong time. Fire. That'd be amusing. Warning, your computer's on fire. Please turn off immediately. Make sure you take the appropriate action and also have the correct facilities. All right. The operating system's in charge of handling all your resources, so it needs to be able to allocate it accordingly. It needs to, well, accounting, which for here is just keeping track of what is using what, so that way it can account for all the different pieces of memory and be able to allocate resources and actually manage your resources correctly. Protection and security, becoming bigger and bigger field. So protection, what does the author call it? Ensuring all access to system resources is controlled. All right, and security is preventing outsiders' authentication to defending I/O devices. So protection is involved in confidentiality, making sure that people cannot, well, actually security is confidentiality, where users have to authenticate in order to read, and protection is
More physical.
in integrity. You don't change something unless you're authorized, or you should be. Oh yeah, the chain is only as strong as its weakest link. All right, command line interface, shells. Has anyone here not used a shell? Beautiful. You okay with shells?
I like shells.
You like shells? Good. Perfect. So y'all know about shells. Y'all know about GUIs. I guess a little history. Mouse, keyboard, monitor. Oh, they don't have the WIMP analogy. Windows icons, mouse, and mouse pointer, essentially. Icons for, yeah, and you can, what is it, various mouse buttons over objects for various different actions, you know, left click, right click, middle click. Of course, with touchscreens, we can do all sorts of different gestures as well. Believe it or not, Xerox came up with the GUI. I think it was late 70s, if I recall. And most operating systems have both a GUI and a command line nowadays. All right, this is what a bourne shell looks like. OS X. I'm assuming y'all have seen these before. Nothing new. Excellent. All right, system calls. This might be something new for y'all. Or y'all all know what a system call is. Getting blank looks. Awesome. Matt?
Make an educated guess.
All right, go for it.
Somebody's calling the system.
Someone's calling the system.
Well, actually, I guess the user's trying to get to the kernel mode.
Okay, sure. That's a good way to do it. That's a good idea. That's a good way to think of it. Yeah, they're basically low-level system. You calling a system function is what you're calling. Very common.
Is that like LS?
LS is a program, and that program is going to do system calls on by interfacing to your computer. So there's read and write, and those are usually system calls when you're trying to read and write from some file descriptor inside of Linux. File descriptor can point to many different things. But usually a system call is something the kernel presents so that other applications can interface in a standard way to the hardware resources. It
So-
is a application program interface. It is an API.
So like, so it wouldn't be like the GUI itself. When you're using a GUI and you do something with a GUI, then it turns around and does an actual system call
Does the system calls? Usually, it's going to be more than one in order to
to
perform.
simulate whatever it was that you were
Right.
doing on the GUI.
Now, when you, for example, if you ever use the standard C library or other libraries in Java, those internally are doing system calls to perform their function as well. So system calls is really down the low level. Let's see. The system call is an API, but usually you have another API on top of it, like the C standard library or the Java standard library. The Win32 API, hopefully no one is programming that anymore. Anyone? Good. That drove me nuts. POSIX isn't bad. Linux and Mac have their own APIs. Java API, everyone should be familiar with that. If you used Java before, that is their API. So why use API rather than system calls? Ooh, that's a great question. Since you haven't seen system calls too much, you probably are hard to understand why, but the real reason for it, APIs, the higher level APIs are always easier to use than the kernel level. The kernels are just trying to provide basic functionality for you. They're not actually going through and making it nice. They're just making it happen. The higher level APIs make it nice, except for that Win32 API. Okay, this is good to explain how detailed these system calls are for an example. So if you want to acquire the input file name, aka you have to ask the operating system, hey look, does this file actually exist? Are we good? The iOS would say, yeah, I exist. Write something to the screen, that's another system call. Accept some input, that is a third system call. Then you acquire the output file name. Write a prompt to the screen, accept the input. That's pretty much how you acquire the two. Then you open it. If the file doesn't exist, abort. Create the output file. If it doesn't exist, abort. Loop. Read from input, write to output, because usually read and write have a set buffer for a certain number of bytes, and you have to keep looping until it fails, and you need to close it, write a completion message to the screen, and terminate normally. This probably looks a lot like what you'd have to do if you're writing in C. And that's usually the case because C is going to be a wrapper on top of system calls. It's really just a standard portable way for doing a lot of them. But system calls between Linux, Windows, and Mac are different. I am not going to go over this. You hopefully will never have to learn this. But this is the Win32 API, which is why a lot of these things just don't make sense. Let's go over to the Linux realm, so it'll make a little more sense. All right, read is eventually calls the system call. File descriptor could be a file, could be standard in, standard out. Remember in Linux everything's a file, so your file descriptor could just be whatever you want. Buffer of what you want it to be read into, and the number of bytes that you want read from it. And it returns how many bytes actually got read. That's all this one does. What does the Windows one do? Read file. Yeah, you got a lot more to do. Bytes to read, bytes read, lab, and then Boolean if it worked. And overlapped is, I don't remember what that one did. Oh, here we go. Indicates if overlapped I/O is being used. Oh, great. Okay. Hopefully you see those two are similar.
The C.
What's what?
The C. Read file C.
Character? There should be an underscore here. Character file? Because you have character files, you have ASCII files, and you have data files. For some reason Windows cares, Linux does not. Windows actually cares a lot. Windows has 10,000 system calls. Linux has just over 200. Just the way they did it. All right, system call. The implementation is definitely hidden from the user because it's part of the kernel. So you just need to worry about, like most things, worry about the API and let the OS handle it from there. Most details of OS interface, yeah, hidden by the API. Great. Y'all are used to this. It's the same methodology, encapsulation. All right. User application, open, system call interface. Kernel actually does the open. The nice thing about open is just to hit home exactly what's going on, by using the system call interface, you don't care about what file system is being used. If it's, what was it, Btrfs, ext4, NTFS, FAT32. You don't care, you just try to open a file. The operating system will worry about that. You also don't care if it's on a solid state drive or a magnetic disk, on a tape drive, on a CD. You don't care about that. The operating system has to take care of that because someone has to. So the OS is actually doing a whole lot of work for you by just providing a standard interface to open a file on any given device or file system. Same thing happens when you do printf. Because it has to write to the screen, you don't care what the video card is. You don't care what GUI. You don't care if they're running GNOME or what GUI is you're running. You don't care about the terminal program that's up. You just want it to be written to the screen. Again, the operating system is going to take care of that. You don't care about the monitor's resolution either. The OS takes care of that. Hopefully you're seeing the OS is doing a lot of work for you. Yeah, a lot of times more information is required than simply identity of desired system calls, so type. You really, when you go and you look up the system calls, and I think my first lab, I'm going to get to it. Couldn't get to it today. Hopefully next week we'll be actually inspecting some of these system calls and writing your own. That may seem daunting at first. It's actually, if you follow the steps, it's pretty straightforward. And then write a little program to call your system call and just make sure it worked. Let's see. Pass parameters registers. You can pass them as block and memory, which is usually what Linux does. Can be pushed onto a stack or popped off. If you've done assembly, you hopefully understand what that means. There's a little stack memory, and that's how it can be stored. Block and stack methods don't limit the length of parameters being passed, which is why they're pretty popular. Although the registers are faster. Okay. You've taken computer architecture, but just so you recall, you've done assembly, you store the address of where the memory is of all your parameters, and then you can go into the memory and actually use those parameters. And that's how you can have any type of length to your parameters. All right, types of call. Okay. The book does go through 6 major different categories of system calls. I don't know if memorizing all 6 of these is actually that useful, but once you see the pattern of how they each work, that is the most useful aspect of this. So now memorizing kind of what these are will be helpful. So fork, what's fork do? Wow, the Windows one's pretty verbose about this.
So the one that does it in a separate thread, does a thread?
No, fork does not create a separate thread. You're on the right track though. It creates a separate process. And it will create a sub-process of your current process. So then you're going to have 2 execution paths that have their own memory space, their own everything, their exact copy of one right after fork. Which is kind of funny because right after fork you have to find out which process you are in your code. Exit, you leave the process, you terminate the process, and then wait. You usually are waiting for some signal to come to your program so that you can start executing again. Windows has the same functionality. They're just called different things. Create process, exit process, wait for single object. Same thing. File manipulation, open, read, write, and close. What else do you need to do to a file?
Delete it.
Delete. Well, you could just open it, and you could open it with the flag truncate and then close it. You can also open it with a file descriptor of deleting this file, and that'll also come back true. There's actually a lot of options with open. That is not what I wanted. How about 2 open? There we go. So you can open up a file, and then there's a whole slew of flags that you can send. Append the file, close on exit, create the file if it doesn't already exist. There's a lot of flags you can send. And what I'm talking about, okay, I'm going through quickly. I'm used to people who are, I guess, system programmers. Int open constant char, the file name, so you're passing the file name, and then int flags, you're going to concatenate these flags together. Being an integer means that you can have 32 different flags. You can also call mode as well. Ooh, that's cool, depending on which open you have included. That was a great question, or a great comment. All right, device manipulation might be a little weird, but IO-octal, or ioctal, I like to pronounce it. What that does, you can read, write, you open and close, but every once in a while it's a lot easier if you send a special command to a device. On a file, you could say, hey, look, jump over to this part of the file. Maybe on a device, you can say, it's a USB device, and you want to say, hey, look, I need you to switch over to this mode. Maybe you're a USB device with 2 keyboards, and you want to be able to select which keyboard you're currently using. Something along those lines, you could select between the 2. ioctal is really a general purpose, just send a signal to a program. And then read and write again. You notice your question would be, are the read and write in Linux the same as the read and write up there? The answer is yes. They're the same functions. They just perform multiple purposes. But notice how in Windows they have extra functions to delineate between the 2. That's just how Windows chose to do it. Notice when I brought up read, you have a lot of flags you can send. Linux prefers to have one function that you can send a bunch of flags to. That's what it comes down to. Information. What's your PID?
Your process ID.
Process ID. So that's going to tell you which process you are. This will also help in determining if you are when you fork, if you're the parent process or the child process. Alarm. Oh, I don't remember alarm. I think that wakes up all your processes that have gone to sleep. There are actually a lot of other information maintenance, but those are some good ones. Communication. Pipe. What's pipe? You remember that?
Take the output of one and put it into the input of another.
There we go. Perfect. So in the shell, when you pipe 2 programs, ls-la, pipe it to more, it's just calling pipe and taking the output of your listing and sending it to another program. For example, I over here and I did ls-dev, gives me a whole list of things. But if I do dev, pipe it to less, now the output's been sent to another program that I can go up and down, because right now I'm running less with the input from ls. So that's piping. All right, the next 2 are with memory map, shared memory. You say, hey, look, I want all our processes to share this piece of memory. Get the memory, map the memory. And last one, chmod, umask, and chown. Does that sound familiar?
Yeah.
Yeah, those are directly, that's exactly what those programs do. They just call these on your file. Again, Windows has their version. Mac is going to have theirs. Although Mac's version is going to look very much like Unix. In fact, I think these are probably the same. I'd be surprised if they weren't.
So is there a way for us to skip the program call for like chmod and just call the system call?
You could write your own C program that does it. But we already have a program. So you can write a program that calls chmod, the system call, or you can just run chmod, which will do the system call for you. Okay, let me take a step back. The next portion of these slides, I really wish they explained what was coming up before they just blurred this all out. We're going to go into kind of a history of how operating systems have evolved with process management or using processes or execution. So MS-DOS, any of y'all played with DOS? Old enough for that? Well, how about the new kids? Nope. Good. I understand. That's a good thing. DOS, the DOS kernel was loaded, you had your command interpreter, done. You wanted to run a process, it ran on top of the command interpreter, and then hopefully you have some free memory. That was it. That's it. It was one process at a time. You're not going to run anymore. Yeah. What?
It was just simple.
It was pretty simple. It was nice and simple in a way. Could get you in a whole lot of trouble, but that's okay. FreeBSD, you might have the kernel, one process, an interpreter, another process, maybe some free memory, and a process on top. So you have processes all along the memory, your memory. That's how BSD does it. That's actually how Linux and Windows do it as well. Which one? Yeah, so this one's a lot simpler. Also, MS-DOS never did any type of virtual memory, so you just accessed memory directly, which was great because you could write a program to overwrite the kernel, and MS-DOS just did not care. It was classic.
That's why you always had your boot disks.
Yeah, always had your boot disks ready. Yep,
That's
boot
what
disk
we
was
did.
always at the ready. FreeBSD, of course, did some protection, and you got multiple different processes. This is far more like a modern operating system. Okay. The point here is, as Chris pointed out, you could write a program that runs chmod for you, or you can just run the chmod program to call chmod, the system call for you. That's all. This is slides really trying to tell you. And just keeps on telling you that. That's nice. All right. This first statement is kind of misleading. Design implementation of OS is not solvable. Well, it's kind of contradictory since we have something running nowadays. Really what it's trying to tell you is, one, it's hard, and two, we operating system programmers never guarantee that their OS is optimal, is the most optimal implementation. There's always ways to improve your code. Hopefully you've realized most programs are like that. Internal structure can differ on operating systems a whole lot. Right. Most of the time when you're trying to design an OS, you want to go with a goal. So users just want to be easy to use, easy to learn, reliable, safe, and fast. Sometimes they want to be designed and maintained, flexible, reliable, error-free, and efficient. Third one that's not up here is security goals. Sometimes people flat out don't care if it's easy to use as long as it's secure. I've learned that that's definitely the military's take on things. I've gotten a program approved that was secure but was not functional, but they were okay with that. As long as it was secure. Good.
It wasn't functional.
Well, no. But it was secure. They wanted their ATO, so we just got it out there, and then we did an ECP to finally make the thing work. It was quite hilarious. The goals are often conflicting. It was great with IV and V. That was my favorite part. But anyways. All right, two terms that you do want to get in your head, make sure you understand the difference, is policy and mechanism. The policy is an administrative document or an administrative policy. It's something people, higher ups, usually say, we'd like your program to always function this way. And that's what needs to be accomplished, what needs to be done. It's your goal. The mechanism is your code, aka how you actually did it and implemented the policy. Please tell me to give me good examples. No. Okay. All right, MS-DOS, written to provide the most functionality in the least space. Doesn't have modules. It was just one giant program. Well, it actually wasn't that big either. Wasn't well separated, quick and dirty. Actually, MS-DOS, the original DOS was called QDOS, which just stood for Quick and Dirty Operating System. and then evolved to MS-DOS, which eventually evolved into Windows. It was quick and dirty.
Oh, yeah, that just slit your throat. Mine was just.
Oh, but it was quick.
Yeah.
Oh yeah.
It's like hit a button. Why did my screen go dark all of a sudden?
It was quick about it.
Yeah, it was.
It was very quick about it.
Oh, that was so long ago.
So lovely. All right. Your device driver, MS-DOS driver, device driver, the system program that you might be using, and then your application program runs on top of it. The big thing to keep in mind is your application program can access your device drivers directly at any given point. This is different than what you're used to because usually there's a system call interface. This one just, it had to know what the device driver, your device was. Or it could try and use MS-DOS's device driver. Instead, we have something called a layer approach. Where's the circle picture? There's a circle picture. The idea is your layer 0 will be hardware, that you have one API on top of it, maybe your system calls. You have another layer on top of it, maybe your language libraries, C, basic, standard C libraries. And on top of that, you might have additional ones, the Qt library, the GDK library, maybe Java as well, and so forth and so on until you get up to your your program running. Why is this one preferred over the way MS-DOS did it? Why is this preferred over not having the layers and just being able to access the device driver directly?
Security, you just said it, not being able to access.
There's security problems, that's one thing, yeah.
Because you can then only have the user only access the outer layer. That's it. They only have permission for the outer layer. And then you've got some administrator that needs to have the access to layer 1. And then very few people have access to all of it.
Sure, okay, that's a great, so security. Any other reasons?
Changing things out.
Okay, yeah, you can change things out. What if your layer 1 was terrible? Just for, we'll do layer 2. What if your standard C library implementation was pretty poor? Yeah, you can just change it out and put it back in. So this is definitely more modularized.
But you're looking for something else, I'll say it.
No, those are actually excellent answers. I just have a third one in my head. So this one's a little hard to see, but portability has been increased. Because instead, back here, oh my goodness. Your application program could interface directly with the device. Meaning that if your device changed, the hardware you changed, your program would no longer work. But by enforcing a layered approach, if the hardware changed, your next layer would just take care of it, and your application program on top didn't have to deal with
Right,
it.
because each layer only knows how to connect to the next
You
layer.
got to the layer above it. Can y'all see any implicit downfall of this approach?
You need all the layers.
You need all the layers. Why could that be a problem?
Somebody changes layer 1, then all the outer layers might not be compatible.
Okay, that is true. That's true. If you mess up layer 1, everyone else goes down. That's a good one.
But if layer 1 goes down, nobody has access to the hardware, so nothing's getting done.
Right, nothing's
If
getting
any
done.
layer goes down.
Of course, yeah. What your point is, if the kernel fails, it's a kernel panic. The system
I'm saying
does.
they change the kernel. It's
Yeah.
not necessarily down.
Mhm.
It still works, but your layer 2, 2, and 3 was expecting
The
a
point is
different
this
layer.
thin line is that everyone should be adhering to the API. That thin layer is the policy, the what you want done. What is happening inside the 2 layers is how we're doing it, the mechanism. Might be another way of thinking of this. But yeah, you have to have all these layers. Does that mean your programs are large or small? Actually, that's a good question. Your programs are actually small, but your operating system is now
The resources
large.
you use.
The resources could be increased, which could lead to performance issues. In general, that's not what happens a lot of the times, because by using a library, you usually speed things up because someone else probably spent a lot more time making it happen.
Well, you're thinking, so the outer layer, the outer layer is usually, I mean, your
Your
largest layer.
application.
So you've saturated with users. Then as you go in and in toward the inner layer, you may have more scheduling conflicts. Well,
I see what you're trying to
I'm
say.
trying to say that you could overwhelm the system because you have too many people trying to access a limited resource. But you can just change that.
I see where you're going. Modern operating systems they have it so that processes can share code. So you only load one DLL, and then or dynamic.
And it's already there.
It's already there, and then
Anybody
all the
else-
programs can link to
Okay.
it because they're not going to overwrite the DLL. It's reading only, so they can read from the shared library, so to speak.
And then it won't be put back until nobody's using it at all.
Correct. You got it. Great observation. Okay. That's really what we're talking about with layered approach. All right, microkernel. Here we go. This is going to be good. I was very sad that microkernel versus monolithic was only a minor slide in this presentation. So the idea is beforehand you're kind of thinking about, let's go back to this picture. Whoa. Where your kernel and your operating systems handles all these things. Signal terminal, file system, CPU scheduling, so forth and so on. The idea of a microkernel is that the kernel is not going to do any of this. All it's going to provide is a mechanism to communicate from one thing to another, and that's it. Then it's going to load modules where one module is the terminal driver, one module is the file system, one module is the signal terminal, one module might be the CPU scheduler, one module might be the disk and tape drivers. Can anyone guess any issues that might be from microkernel? Or maybe we should ask this differently. Why would people want to do a microkernel?
Speed.
So speed. Why do you think it would improve on speed?
If I only want to access one resource or two resources, then I only want to deal with one of those, one or two. I don't want to have to then
Okay.
I don't want the kernel to spend time trying to figure, okay, what resources it needs. If I put the particular call in, the kernel says, okay, here you are, and you already go to that section.
Okay.
I mean,
Okay. I guess my question is, how is that different than a monolithic kernel where, I mean, you still do the system call interface, and if you would jump to it, but with a microkernel, you do a system call interface, and then it translates that into a module that's back up in user space that does it, and then translates that back to the
Okay.
program. That's what's going on.
Would you, once you're doing it though, you would be the only one to be able to use that, period. Nobody else would be able to get
No,
it?
you'd be able to, because the point is all these tasks are actually user space tasks now. It's just the microkernel is handling how you communicate between different user
So
processes.
the microkernel would just put out 2 or 3 different modules for the same thing? What I'm saying is if you use the terminal drivers,
Mhm.
you got a kernel for the drivers or whatever.
You have a device user space program for the terminal drivers that the microkernel knows how to hook up to anyone that needs to use it.
So you can still have multiple users then?
Oh yeah,
Okay, never
oh
mind.
yeah, you can have multiple users. This was actually a really, really hot debate for a long time and still is.
So it wouldn't be faster? It just depends on how it's set up?
Benefit, yeah. So the benefit, yeah, it's actually not, it's slower. The benefit, it's easier to extend a microkernel because you just switch out the module you're using for your terminal device driver. You don't have to go in and edit a monolithic kernel. You can port the operating system newer architecture because the microkernel is actually not doing anything architecture specific. You just have to update your modules. That's all you have to do. I am going to say that the next bullet point is wrong, but some people think it's more reliable because less code is running in kernel mode. While I get what they're trying to say there, by having to do all this communication, yeah, I think it becomes less reliable because it adds more points of failure. they consider it more secure because less code's running in the kernel mode. In theory, that's correct. I haven't seen in practice whether that's actually true or not. I also have not seen a paper proving one or the other. And I was really sad that that was the end of it. So I'm going to pause here because we're going to talk about an important debate that happened over this.